Voltaic cells, aka batteries. Voltaic cell is a device that uses a spontaneous reaction. This is important, all right? So voltaic cells are spontaneous reactions. Make sure you know that. Very important. Redox reaction to create electrical current. So we think about spontaneous reactions, and we know that something loses electrons, something gains electrons, and we use that current to power something like our car battery, or like our AA batteries, or C battery, or whatever. Voltaic cell contains the following: 2 electrodes and an electrolyte. So first of all, electrodes are the solid conductors. So they, for example, okay, they would be the terminals or the battery posts on your battery car. Okay, they're the solid conductors, so they are the 2 solid things. Electrolyte is, of course, the aqueous solution. They're aqueous conductors. Aqueous solution implies, of course, ions in a solution, yes? In car batteries, it tends to be a mixture of sulfuric acid, yes? You know, when you shake the battery and you hear that right? Yeah, not like that at all, actually. When you shake it, you can hear the sloshing in there. That's sulfuric acid. So don't open it up and go, oh, sulfuric acid. Splash it in your eyes or something, okay? The cathode is the positive electrode, okay? So the cathode is something we call the positive electrode, and anode, of course, is the negative electrode. You have the positive terminal and the negative terminal on your battery. That's called the cathode and the anode, all right? Here's an example of maybe a C battery here, for example, and you might say, well, where's the aqueous solution and all that other stuff? Well, it's a little more complex than that. That's Duracells and Energizer's patent pending thing on there, okay? But basically, that's what we're going to talk about. Voltaic cell design. Voltaic cells can be built from 2 half cells, all right? Each half cell contains an electrode, so a solid conductor, and electrolyte, so some type of ion, all right? The simplest half cell is a chunk of solid metal with the metal ion solution. So a strip of, you know, when we did we went to the lab and we did the copper strips and the zinc and the magnesium, and you guys dipped them. We did that spontaneous, not spontaneous reaction stuff, right? Remember? Okay. That is the simplest half cell right there, okay? You take a solid chunk of copper, that little plate, that shiny bronzy looking plate there, that copper, and you stick it in a copper 2 ion solution, for example. That's what we would consider a copper half cell, okay? So, simplest is that. The 2 cells, of course, but listen, if that's in one, so if you had copper chunk stuck in a copper 2 ion solution, that's fine, that's great. But that's only half of it. You need another half so that there's a transfer of electrons between the 2, okay? And we'll draw these for you, so just be patient. How do you connect those 2 together? There has to be some kind of connection. We use a wire connecting the 2 electrodes. It may be run through a voltmeter, so you might see actual volts measured on that voltmeter, okay? You also have what we call a porous boundary. It's called a salt bridge or a ceramic cup connecting the 2 electrolytes as well. So we're going to draw this right away, and you'll see what all this looks like. All right? So what does the general design of a voltaic cell look like? Well, you guys have some space there. Let's do a little diagram. Oh, let's go with blue. Okay. You guys got some room there, yeah? All right, here we go. So I'm going to do them the same way. I do them the same way all the time, and I'll tell you why. Because next week, we're going to talk about cell notation and things like that. And I always like to go left to right with that, because that's kind of how cell notation goes, left to right, and it matches up quite nicely if you always do them this way. Now, does it matter if you take that and you flip it around? And the answer is no. Do the electrons move in a different way? No, they always move in the same direction towards the same cathode or anode, okay? But just be aware, of course you can flip the 2 beakers around, it doesn't matter, but your diagram may be a little different then, that's all. still can do it. It's fine. I like to start with a beaker here and said beaker over here. We're going to have these in a solution, of course. We are going to have solid conductors, the electrodes. So I'm going to have one electrode sticking in over here. I'm going to have another one sticking in over here. Okay, like so. So I have two electrodes. I have the electrolyte part at the bottom. Okay. I like to do it this way. So I like to put the anode here. Okay. And I like to put the cathode on this one here. All right. You need a wire to connect the anode and the cathode, or, you know, in an actual battery, I'm sure it'd be something different, of course, but you need some type of wire. There might be a voltmeter here, perhaps. So it might actually, you know what, let's skip that. That's fine, don't worry about that. Let's just keep it nice and simple here. So there might be a voltmeter that measures volts, of course, et cetera, okay? So you might actually see that in between those two. So it, you know, the little dial or whatever. Or if you guys did, if you guys ever play with, you know, they have digital ones now, yes, where you can hook up the two things, test batteries and stuff like that, yeah. So it could be something like that as well, okay? Now, the anode, okay, let's think about this for a second. Well, what if I told you, which ways do the electrons go, I guess, is the question in this case here. And the electrons go towards the, you know, it's actually in your notes coming up here. Electrons always travel towards the cathode here in a Voltaic cell. Okay? So, electrons travel towards the cathode, like so. If that's the case, let me ask you a few questions before we get too far here. What can you tell me about the anode then? What can you tell me about the anode? The anode is what? Gaining or losing electrons? Losing, correct? Yes? So if the anode's losing electrons, what kind of reaction is undergoing? Oxidation, yes. Therefore, it is the what? SOA or SRA? SRA. Okay? Hey, look, you guys already know stuff. Hey? Look how far you came already, eh? So yeah, the anode is being oxidized. It's losing electrons. In fact, that would be your oxidation half reaction. The cathode is doing what? Gaining or losing? Gaining, right? Gaining electrons. It's being reduced. So you would find the SOA for that, right? Oxidizing agent, right? Okay. So if the anode is a solid chunk, right? Actually, let me do this for you here too. Where'd my data booklet go? Right here. Let's think about this for a second. Where would I find the anode probably in this chart here? Top left or bottom right? Bottom right, yes? Because it's being oxidized, yes? So I'm going to start working my way up here. If it's a solid chunk, it's going to turn from a solid chunk of something into an ion, yes? Probably, because it's going to give off those electrons. Now, so what I'm going to say here is a solid, this anode, whatever it happens to be, that's all I'm using A for, I don't know what that is, that solid anode is turning into a 2 positive aqueous, for example. And I just picked 2 positive because I felt like it, and you can't change me. So there. Okay? So deal with it. It could have been 1, 3, I don't know. What doesn't matter. Okay? So A solid is turning into A2 plus, and those electrons are being lost. It is in this case here, it is the one that's most likely to lose electrons, yes? Okay? Those electrons are going over here. This cathode is the most likely one to gain those electrons. So over here, I got some, this is not carbon, this is the cathode solid here. And over here, let's say I got C2 plus aqueous. Well, that's going to add itself onto there to make C solid, right? What's most likely the cathode half reaction? Well, C2 plus 2 electrons gives me C solid, right? Yeah, because it's being reduced at the cathode, yes? Those electrons come over here. Basically, they come into this cathode here, and the C2 plus and those electrons meet up, and they add on to that, okay? And we'll talk about that in a second here, all right? That's what a typical, we're missing a few things yet, but that's how this battery or voltaic cell would work in this case. By the way, you know how many voltaic cells are on this sheet? The answer is lots. Because anytime you have a spontaneous reaction, it's voltaic, yes? So anything that looks like this, right? Top left, bottom right, top left, bottom right, top left, bottom right, top left, bottom right is a voltaic cell. Okay? Yes? There's lots. Okay? So that's what you need to be thinking of now is voltaic cells, spontaneous. How many spontaneous reactions are there here? Lots. Okay? Lots. All right? Now, this part is the salt bridge, we call it. And I guess we might as well talk about it now. The salt bridge is named a salt bridge, or in actually when we go to the lab, you guys, when we go to the lab, we're going to use a ceramic cup. Okay? Same thing. We don't have well, we do have fancy bridges, but we use ceramic cups because it's easier. Whatever, doesn't matter. Basically, the gist of this is this. When you draw these, we're going to ask you to draw a cell. You've got to draw the salt bridge as well. This is called, because it's bridges, and it's full of salt. And you might say, salt? Yeah, an ionic compound is a salt. So any ionic compound is a salt. We know that, right? Acid, base, gives you water and a salt, ionic compounds, right? So any ionic compound is referred to as a salt. Could it be table salt? Could it be sodium chloride? It could be. Okay, probably not, but it could be. All right. The thing with the salt bridge is the anions, because remember, a salt bridge is ionic compounds, ionic compound made up of positive and negative ions. The anions always go to the anode. It's easy, actually, guys. Anions go to the anode. Cations go to cathode. Okay? How about that? So that's your general diagram for every voltaic cell we'll draw. Okay? Voltaic cell. Okay? The purpose of the salt bridge is this. Why do we have the salt bridge? And I'm just going to explain this. Really, ultimately, guys, you know, how many questions are you going to get about salt bridge? Probably none. Are we ever going to tell you what's in the salt bridge? Maybe once, maybe. You know, if we told you it was potassium chloride in here, potassium chloride, well, the potassium ions are going to go this way and the chloride ions are going to go this way. Okay? That's pretty much it. You know, other than that, what else do we ask you? Not much. We don't really care about that too much. We care about the actual cell part. Okay? What's the salt bridge's purpose? What's it there for? Well, what happens is the anode is losing electrons and becomes A2+. So it's losing electrons. Let's say this has been going on for 5 minutes. It's losing electrons, losing electrons. We're getting A2+, A2+. 10 minutes passes, same thing. 15, 20, an hour passes. We're losing electrons. We're getting A2+s here. What happens down here? We get a lot of what? Not a trick question. We get a lot of A2+s. Yes? Well, what's going to happen after a period of time? A2+, right? After a period of time, do you think, yeah, I realize that this is the, you know, this is the SRA here, right? And this is the SO, I know that. And that one wants the electrons and this one wants to get rid of them. But after a period of time, when they get so many positives down here, are these actually going to want to let go of their electrons and give them over to that one? It's probably going to slow down, right? Or it's probably at least, it's going to slow down if nothing. Eventually, it may even decide to stop that because it's going to be so positive in that solution, it's going to be holding on to those electrons too much. And I realize that the cathode wants them, but after a period of time, it's just going to be like, well, you know what? We need to slow this down a bit because look at all the positives, guys. All the Bacheks are down here, right? And they don't want to let go of the electrons. So, that's what's going to happen. So the salt bridge is there for that reason. What happens is the anions here will combine with the A2 pluses and neutralize that out. So the chloride is maybe a -1. It doesn't matter what the ratio is. The chloride is there to kind of help neutralize that solution, right? It helps keep this from building up to be all positives. Now you put in some negatives in there, and the positives and negatives kind of help neutralize each other out so that the electrons are still free to go. Okay? That's really the job of that salt bridge. Okay? Electrons come over here and they're gained there. Okay? So that's your basic general diagram of a voltaic cell. All right? All right. The SOA is always reduced at the cathode, half cell. So once again, you have reduction at the cathode. It's gaining electrons at the cathode. And you're losing electrons. It's always oxidized at the anode. All right? If you want an example of this, a specific example, we have something called the Daniell half cell. It's made up of copper and zinc half cells. All right? Now, the Daniell half cell is named after the guy who kind of came up with this here. He did some research on this or whatever. It's just a specific example to actually show you what a copper and zinc half cell would look like. So when you get these, you're still going to have to do this. You're going to be like, oh, how are we going to use first lessons to do these half cells? Well, just wait. Hey, that we did that all for a reason. Think about it. If we have a zinc half cell, we obviously need a zinc electrode. So we're going to write that down. In other words, what I'm asking you is to predict the half reactions that are actually taking place here, so we can properly put them on the anode side or the cathode side. So we have zinc. We have copper solid as well, because we know that's our other electrode there, right? The electrodes are solids, so they have to be zinc and copper in this case. A zinc half cell. Well, geez, let's think about this. If zinc was a half cell, remember we said a half cell involves a metal and probably a metal ion. What would zinc probably form as a metal ion? Probably zinc 2+. So we better write that one down as well. So this is where it's a little different here. Okay? So we got some zinc 2+. Well, what about copper? What if I just had some copper, what ion is it most likely to form as well? And the answer is copper 2+ is the most common one. And of course, you're going to have some water in here as well. Okay? Obviously, that's how you're going to make these solutions at the bottom, the electrolytes. So what you need to do is start in the top left and start working your way down. Okay? Well, so what's my SOA in this case? Well, it's copper 2+ is my SOA. Okay, you're going to look in the data booklet, top left, working your way down. Copper 2+. So copper 2+, I'm going to write it out from my data booklet here, guys. Plus 2 electrons gives me copper solid. Okay? Where reduction takes place, where is that going to take place? It always takes place, reduction is the cathode. So what we're going to actually change this to now is we're going to put down a C here for cathode. Okay? It's actually the cathode is where that's taking place. It's gaining that electron-y thing there. Reduction is the cathode. Okay? And that's where it's taking place. At the cathode, we're gaining electrons. Okay? What's the oxidation half reaction? Let's start in the bottom right and start working our way up. And we find that probably, right? Well, not probably, it is. SRA is zinc solid. So zinc solid becomes zinc 2+ and 2 electrons. Okay? If it's being oxidized, that's at my anode. So I'd put an A down here, or anode, is what we're going to call that now. So we're changing the name of reduction half reaction to my cathode and oxidation half reaction to my anode. And we're going to add them up just like we did before, right? And before we call it the redox reaction. Okay, well, we can still call it that, but we're also going to give it a new name. Copper 2 plus and zinc solid gives me copper solid and zinc 2 plus. Okay? So we would call this, of course, earlier we called this the redox reaction. Now we're going to call it the net cell reaction. The net cell reaction. In other words, when we add those two half cells together, that's the overall net cell reaction that we're going to actually be taking part in here. Okay? Net cell reaction. What would that look like? Well, now that you know what the cathode looks like, what happens where it's being reduced, and you know what the anode is going through, we can draw this. So we're going to do that. That's the purpose of this. Actually, this was just all extra stuff here. But we're going to draw it. So half cell, half cell. Let me get rid of that for a second. We got solid, electrode, electrode, wire, electrons moving. Okay. What's at the anode? Well, the zinc is at the anode. Zinc is the most likely to lose electrons, so I would write here zinc solid. Okay. It loses electrons to form zinc 2 positive in this water solution. Okay. So you'd have to have this in water, of course. Electrons move up and over, and it seems to me like copper solid here. Now remember, these have to be solid chunks, okay? So the copper 2 plus is gaining the electrons. Where's the copper 2 plus? Well, you'd have to have a copper 2 plus solution down here, and it would add on to there, okay? Of course, if we didn't have a salt bridge, this might slow down or stop. So we need to add in a salt bridge here. And we're just going to put here anions go this way, cations go that way. Let's go that way, that way, that way. Yeah. Anyway, stupid catchy songs, right? Okay. All right. That away, that away, that away. He's still sleeping. All right. So that would be your Daniell half cell. That's a specific example, but that's what we're going to do probably starting next week early. Okay. So anions go towards the anode, cations go towards the cathode, of course. If you want to label these, so anode here, right? For sure. Cathode there. Cathode would be the positive terminal. The anode would be the negative one. Yep. Yep. Okay? So that's your basic Daniell half cell there. Okay? The arrows are important. You need to show me that the zinc is basically turning into zinc 2 plus because it's losing electrons. So I want to see the arrows, guys. Exactly what I have here. Electrons go up, and I want to see the copper 2 plus gaining electrons with those electrons coming in, okay, to gain more copper there. Things that you would see there, well, before that, of course, we talked about this. Copper 2 plus is the SOA. It's the one that's being reduced. Zinc is the SRA. It's the one that's losing electrons, okay? The cathode half reaction, the anode half reaction, the net cell reaction, okay? All that stuff that we just did, which you guys know how to do, right? Electrons, I don't know what's the problem today. Electrons travel through the wire from the anode to the cathode. Of course, I show you that with the arrows. Okay. In the salt bridge, anions flow towards the anode, cations flow towards cathode. Some things that you would see happen here. If you go back to your little diagram here, things that you would see happen. Well, let's see. We've got a chunk of zinc here. What's going to happen to this chunk of zinc? Well, it's changing from zinc into zinc 2 plus in a solution. What's going to happen over time is that this is going to decrease in mass. Okay? this solid part. Now, do you still have zinc? Yes, you do, but it's changed form into 2+ ion. So there's still zinc in there, but if you took this out after a period of time, you would have less solid zinc to weigh. This would get used up, okay? So the mass of the zinc is going to decrease. In opposite fashion, copper 2+ is going to be changing from copper 2+ into solid copper, right? There's already copper here. We're just changing forms again. We're gaining electrons to gain more copper. This mass would actually increase, okay? The third thing that you could probably see here, zinc doesn't have a color associated with it. Zinc 2+ doesn't have any colors. Copper 2+ is blue, okay? It's that pretty blue that everybody likes, right? Reminds you of clear blue ocean mountains. Yes, ocean mountains. Copper 2+ is that pretty blue ocean colored mountain stuff kind of thing. And it would be used up because you're changing copper 2+ into copper solid. So this blue color, that pretty blue, would start to fade over time. And you would eventually get back to clear perhaps if you used up all the copper. Or eventually it would get to look like it's clear, although there might still be some in there. But it would fade over time. Okay, you'd be using that copper 2+ up to change back into copper, okay? Alrighty, so those are some things that you would see with that half cell. Here's an example. Yours isn't as nice as mine, but here's an example of kind of what those two electrodes would look like after a period of time. This zinc, like I said, would be kind of dissolved, I guess you could say, or eaten away at, because the zinc, that solid zinc, was changing into zinc 2+. Now you can't see the zinc 2+ because these have been pulled out after a period of time. This copper here looked like basically this rod here, but now you can see that there's more copper added onto it, been plated onto it, okay? And then we're going to talk about electroplating in this unit, you know, like chrome bumpers and stuff, yes? That's this process, right? Electroplating, electrons plating, okay, stuff onto other metals. So we'll talk about that eventually, and all that other good stuff. Corrosion, what happens, how does stuff rust, etc., etc. How can you prevent rusting? All good stuff. Okay? What do batteries look like? Oh, hey, this is your spontaneous reaction. So let's see, what happens to your car battery? We'll take spontaneous reaction. Let's say you have a battery that for quite some time. What happens to it? Where you actually reverse the flow of electrons by adding power, like recharging your phone battery. Everybody knows that. Okay? Heaven forbid we leave them alone. Yes. And your phone battery is an electrolytic cell. Okay. If you're using it right now, you're doing a Voltaic cell. It's a Voltaic cell. When you go to recharge it, it's electrolytic. You have to know the difference between those two terms, which we'll talk about. Right now, you need to focus on Voltaic. That's all. Eventually, when you plug it in, it becomes electrolytic. We reverse the flow of electrons, okay, and you charge it back up. So it's charged again. And then you unplug it, and it's voltaic again. What's that? See? In your car, you use the battery, you drive it, and the alternator is charging it back up. Yes? Okay? Things like that. All right, good. Done. We got time?